Hello, everyone. This is lesson number 14, and we're going to be talking about intro ring theory. So today we're going to discuss the basic definitions of a ring, a field, an integral domain, and certain properties of rings. And basically every video from now on is going to be dedicated to ring theory instead of just group theory. So yeah, so let's get started. So in discussing group theory, you might have encountered the following objects, which are all groups as we understand them. So the following are groups. So we have the integers, real numbers. We also have like maybe n by n matrices with real entries. We have maybe z mod n. And then also maybe like polynomials. And as we've discussed, all of these are groups under addition, right? So you can add and subtract any two integers, add and subtract any real numbers, add and subtract matrices, integers mod n, and polynomials. But when you think of all of these objects, you usually think of another operation on top of them. In fact, all of them also have some notion of multiplication. So all of these also have a times operation alongside the addition operation. Now, maybe you'll say, okay, but the times operation doesn't necessarily have inverses. It doesn't make it into a group. And you're right. For all these examples, it doesn't. In some cases, it might actually. But in almost every single case, it doesn't. But not every single object we've encountered has this property of having both an addition and a multiplication. And so our goal from now on is to study such objects. Study objects that have both addition and multiplication operations. And our basic question is like, what more can we say about them outside of just being groups? So we already have all of group theory, and we're adding on this extra assumption of having this times multiplication or times operation. And our goal is to say, well, what added structure do we get? So the first step in developing the theory is to just make a definition. Okay, a ring R is a set with operations plus from which takes two elements of R and outputs an element of R, and times, which I'm going to write as this little dot, which takes two elements of R and outputs an element of R. And these got to satisfy a couple of properties. Okay, the first property is that if you take my ring and you just take it under addition, then this is an abelian group. Abelian group. And if you recall, every single group has an inverse, and so we're going to call the additive inverse 0. And note that additive identity 0. Note that I'm calling it additive because as opposed to maybe multiplicative, so we can differentiate the two. Identity 0. Okay, that's very natural. Okay, and so that kind of handles our plus operation. What about the times? Well, in all of our examples, we know that times is not necessarily a group, but it does satisfy some other properties, such as I'll write it as cross here. Times is associative. We also require that there exists a additive or multiplicative identity is the multiplicative identity. And here I'm going to maybe diverge from some textbooks like Dummett and Foote, which define a ring to not necessarily have a 1. Such rings are usually called like unital rings. But I'm going to define my rings to have 1. There are some cases where there are rings which like don't have 1 and it's helpful to define it. But usually those are called RNGs, so you just kind of remove the I. Okay, and then the final assumption is we kind of want a way to relate both my addition and my multiplication operations. So I don't want them to be completely distant concepts. I want some way of combining them. And the way to do that is we just have our rings satisfy distributivity. Which basically says like A plus B times C equals A times C plus B times C, and A times B plus C equals A times B plus A times C. Very simple. And so that's it. That's all you need for a ring. Abelian group. Multiplication is associative and has an identity, and you have distributivity. Okay, so let's make a couple observations about this definition. And then we'll start to like work with some more concrete examples. So an observation which I've been talking about is that there are not necessarily multiplicative inverses. Not necessarily multiplicative inverses. So a classic example is like the integers. In the integers, if you take like 2, for example, there does not exist like 1/2 in the integers, right? And 1/2 would be your multiplicative inverse, but that's not there. To do that, you would have to go to the rational numbers. Another example is like if I took n by n matrices, not every matrix has an inverse, only when the determinant is 1. So if I took some matrix such that the determinant was, only when the determinant is non-zero. So if I took some matrix which had determinant 0, then I know this guy is going to not have an inverse. And so I don't necessarily have a multiplicative inverse in this case, but it's still a ring. And so we kind of don't require this assumption, so rings can have some kind of added structure to them. When you require that every ring has a multiplicative inverse, you then get a different definition, which is called field, and we'll get to that. But it happens to be more valuable to not include that definition and study the theory in this way. Okay. Second observation, which sounds kind of silly, but it's basically that 0 and 1, which are kind of the only elements we've actually specified and required to be in the ring, are not necessarily distinct. Even though it seems like they should be. But luckily our intuition holds up almost all the way, because we can prove a quick proposition which just says if 0 equals 1 in my ring, then my ring is just identically 0. In that 0, if the multiplicative and additive inverses were really the same guy, then actually my ring only has one element and it's just 0. Okay, let's do a quick proof of this. So suppose 0 equals 1. Let me take any element in R in my ring. And I know the multiplicative identity satisfies 1.r equals r. Okay, so now I have r on this side. I want to show r is 0. So I'm going to rewrite 1 as 0. Okay, well, this guy equals 0.r. But 0 times anything is 0. So thus I get r equals 0, as I wanted. Thus, r, every element is 0, so r is just 0. And if you want to show why 0 times r equals 0, it's a pretty simple exercise. Basically, you just say 0 equals 1 plus negative 1. And then you get 1 plus negative 1 times r equals r plus negative r by distributivity, and this is just 0. So 0 times anything is 0. Okay. So luckily this like kind of trick of 0 and 1 not necessarily being distinct really only happens in a very trivial case. Okay. And then maybe just a couple other exercises for you to get used to working with rings. I recommend you just try these out. So for example, I kind of use this fact here, but the additive inverse of a, which I'm just calling negative a, is just equal to negative 1 times a. And that kind of follows from this exercise up here. Negative a times b is equal to a times negative b, which is equal to just negative a times b. And then finally, like negative a times negative b equals ab. All this is just saying is that like multiplications, like negative signs kind of work out how you want. If you have two negative signs, you get a positive. If you have one negative sign, you can kind of move it around, so on and so forth. Okay. So when we study rings, it happens to be like kind of standard that we usually assume. So we assumed like the addition operation was commutative, and that's just kind of out of convenience. And it's also usually out of convenience that we assume the multiplication is also commutative. Otherwise, it kind of makes some of the definitions a little messy. And for the rest of the YouTube series, I'm not going to be really working with non-commutative rings. So let's just make this a definition. A commutative ring is a ring R where my times operation is commutative. In that like A times B equals B times A. And that's true for like the integers, for the real numbers, for polynomials, for Z mod n. It's not necessarily true for matrices. And so, yes, you can argue that maybe in that case we're talking about a non-commutative ring. But it's just not something that comes up very often. Okay, so like I said, from now on, every ring is commutative unless stated otherwise. Unless stated otherwise. So yeah. Okay. So the fact that we don't require every element to have a multiplicative inverse gives a richer structure to rings like I was talking about. So it allows us to introduce some definitions which may have been trivial in the case of fields or just like a group. Okay, so first definition is an element. We kind of want to look at, like, okay, not every element has a multiplicative inverse, but some of them do, right? So like some matrices do have an inverse, or some integers do have an inverse. In fact, it's 1 and -1. So an element R in my ring is a unit if there exists R inverse in R such that R times R inverse equals 1. Okay, very simple. And then we also denote this A cross as a, R cross as a subset of R to be the set of all units in R. Okay. So like a basic example is if I'm looking at Z cross, so this is all units in the integers, this is going to be plus or minus 1. For example, the inverse of 1 is 1 and -1 is -1. And if I'm ever larger than 1 in magnitude, there's not an inverse. Maybe like if you're looking at the units in n by n matrices, you're looking at GLN R. So every matrix that doesn't have that has non-zero determinant. Now this is a weird example because it's a non-commutative ring, but that's besides the point. Okay. And so going off what we were talking about earlier about fields, we can now define if every element except for 0 has a multiplicative inverse, meaning that every non-zero element is a unit. And the reason why we don't include 0 is because 0 times nothing will ever get me to 1, because 0 times everything is 0. So if everything is a unit, then we call R a field. Nice. And the idea here is that basically in fields we have division. Which is to say that, like, I mean, division is basically like if you're doing 2 divided by 3, this is like equal to 2 times 3 inverse, or like 2 times 1 over 3, right? And so when you have multiplicative inverses of every single element, you can now basically do division in your field. So that's what's nice about having a field. Now some weird stuff happens. We also have some non-intuitive kind of elements. So units are like you expect them to occur, and they're very natural. But there are also some unnatural kinds of elements that happen in rings. Some unintuitive elements. Unintuitive. Okay, so the example I'll bring up today is zero divisors. So an element R in R is a zero divisor if there exists T in R such that R and T are both non-zero, but R times T equals 0. So you might be saying, if you thought about like the real numbers or the integers, I mean, there's no such numbers where you can multiply two random numbers together and you get 0. Like if you multiply 2 and 3, you're never going to get 0. But this is saying is that in some rings, there exist these things called zero divisors, where you can take two guys which are both non-zero, but they multiply together to be something which is zero. It happens to be that these kinds of elements show up all the time and are particularly important. So let's discuss some basic examples to maybe make them more intuitive. So suppose n is a composite integer. Composite. Then z mod n has a zero divisor. The idea is that n is composite means n equals a times b, right? And if this is the case, and we know that a and b are both less than n and larger than 1. That's what it means to be composite, which means that a and b are both not 0 in z mod n. But a times b equals n is equal to 0 in z mod n. Thus a and b are both zero divisors. Okay, another example. If I look at 2x2 matrices, and then I multiply this guy by maybe like this, these guys are both non-zero matrices, but when you do out the multiplication, every single entry is going to be 0. So these guys are also zero divisors. So 2x2 of R has zero divisors. Okay. So I bring up units and zero divisors because they're kind of like, they have some interactions, but they're kind of like distinct ideas, which like don't agree with each other. They don't like each other. So units really don't like zero divisors. And this is to say, if R is a unit, then R is not a zero divisor. Okay, this is not too hard. Let's do it. So if R is a unit, we want to show R is not a zero divisor. So suppose R times something equals 0. So suppose R times t equals 0 for some t in my ring R. Now I need to use the fact that R is a unit. So I'm going to multiply both sides by R inverse. But recall that anything times 0 is 0, so this side is still 0. And R inverse times R is just 1, so this is 1 times t equals t. And then this must be equal to 0. So I get that t is 0. And this contradicts being a zero divisor, right? Because if you're a zero divisor, you need R times t to be 0 and R and t both non-zero. But if this is ever 0, we've shown that t has to be 0. So R is not a zero divisor. Thus, R is not a zero divisor. So yeah, like maybe my intuition is like units and zero divisors really don't like each other. They're kind of like enemies. And because zero divisors are kind of funky, they kind of ruin a lot of like the math we want to do with rings. We kind of add an extra assumption sometimes to our rings, which is called being an integral domain. So R is an integral domain. Integral domain. If it has no zero divisors. Okay, great. Then maybe some examples of integral domains are, like we said, the integers, the real numbers, real polynomials. If you multiply any two polynomials, they're definitely not going to be 0 unless either polynomial is 0. So integral domains are super, super common, and they're really nice to work with. In fact, you'll probably see for most of the ring theory you'll study from now on, you'll work with integral domains. And especially if you go off to study other fields like algebraic number theory, you'll definitely be working with integral domains. If you go to like Galois theory, you'll be working with a lot of fields which are integral domains, stuff like that. Okay. So to end off on our like intro to ring theory discussion, we're going to talk about one like pretty cool theorem, which is pretty helpful in practice, which says if you are finite and you're an integral domain, then you're a field. So any finite integral domain is a field. And so what you should be thinking in your head is finite means maybe you kind of look like something like z mod n. Like this is not like a great intuition, but it's like maybe should kind of help you a little bit. And then integral domain tells me that n is prime. Because as we discussed, if n was composite, then there were zero divisors. So if it's an integral domain, then n is prime. And we know if z mod n where n is prime, then you've probably heard that this is a field. Z mod p is a field. So maybe that's like a basic example that you could have heard of, that you can think of as intuition for this theorem. Okay, let's do the proof. So really the key property, integral domain kind of is like what lets the whole proof work, but really like the main property is that you're finite. So that's what we're going to use. So like just being an integral domain really doesn't tell you that much towards being a field, but really being finite restricts you a ton. So take a non-zero element in my ring. We want to show that it has an inverse. So want to show there exists a inverse. Okay. So consider the following set. I'm going to take a squared, and I'm just going to keep on taking powers of a, so on and so forth. Now, since since R is finite, eventually this list is going to have to loop back on itself, right? Because the list is finite, the list goes on forever, but the ring is finite. So there's not infinite elements in this list. So eventually it has to loop back. This list loops back. What that means is there exists n such that a to the n equals a to the m for some m less than n. Or you could say that like a to the n is in the list a squared, a to the n minus 1. So it's somewhere in here, and I'm calling the thing that it is a to the m. Okay. Now if I subtract a to the m over, I get a to the n minus a to the m equals 0. Now the nice thing about rings is that I have this multiplication. I can start to do factoring. So this implies that a to the m times a to the n minus m minus 1 equals 0. So you notice I've written this as a factorization equal to 0. And this should instantly tick off in your head integral domain, right? This is where I need to use integral domain. I have two things which multiply to be 0, which means that either one is 0. So either this a to the m is 0 or a to the n minus m minus 1 is 0. But a is not equal to 0 by assumption. So this is not 0. So since a to the m is not 0, I know that this other term has to be 0 because I'm in an integral domain, which means that a to the n minus m equals 1. Okay, now I'm getting somewhere that's very close. Okay, so this part's a little messy, but we have to do it. So if n minus m equals 1, so there's kind of a difference of 1, then this implies that a to the 1 equals 1, or a equals 1. So a is definitely a unit. If n minus m is greater than 1, then this implies that a times a to the n minus m minus 1 equals 1. And this is some number which is greater than 0. So a has an inverse, and it's equal to a to the n minus m minus 1. Thus, a is a unit. Okay, so we get that every single non-zero element is a unit, so R is a field. Proof complete. Great. Okay, so that'll conclude this intro to ring theory lecture. We're now going to go deeper after this into stuff called ideals and subrings and what are maps between rings and all of that stuff. But I'll leave some exercises for you to try on basic ring theory. Okay. First exercise. Find an infinite ring which is not an integral domain. Second exercise, if R is an integral domain, show that polynomials over my ring is also an integral domain. And all this object is just polynomials in X, where the coefficients are in R. And this is not necessarily the real numbers, it's just some ring. Okay, final exercise is you need to determine the units in the ring Z adjoint I, which is the set A plus BI, where A and B are integers. And this is called the Gaussian integers. And you just need to find all the units in this ring. Okay, thanks for watching.